We are Group 15 and our project is an Internet of Things or IoT smart doggy door. While budget for this project was a concern, our goal was to focus on a system that had many features. We wanted the system to be easy to use, such that after installation, the user can start using the door right away with as little hassle as possible. Due to the system's reliance on software, it would be easy to modify or even add additional features for future updates. These features could include changes to either firmware or on the mobile application itself. Another objective was to provide a way that the user could actually control the system remotely by adding an interface that most people have quick and easy access to. A goal that was important for us was to make collars to be as cheap as possible. Many animal collars can be expensive and tend to break with little use. However, we want our system to work easily not only with multiple animals but without cost being a concern to the consumer as well. The door was powered from an AC power source. However, despite power loss, we wanted our system to still operate. Therefore, the system was made able to operate with the assistance of an external battery for an additional period of time. Finally, to assist with dog training, we provided an auditory cue that will notify the dog if it can successfully pass through the door. If the cue does not play, then it is presumed that the dog cannot pass through. For our system to support a variety of animal sizes, we required the inner part of the door to be a dimension that would fit most medium-sized dogs. To ensure that the system is compact, some technologies had to be disregarded. Even though the door could have been implemented in other ways, it would have been constructed at the expense of doubling the height or length of the current dimensions. While the length and height are only slightly larger than the flap dimensions, the width is substantially larger, which ensured that all components could fit in the door. The flap had to be able to withstand a force of 63 Newton per millimeter squared, so it would not only be secure, but it would also be durable as well. When a dog approaches the door to go either inside or outside, the collar had to be read by the system from up to a meter away. The time at which the tag is read, the database must be queried and the door must be unlocked in under 4.5 seconds. The infrared sensors, which activates a camera and detects dog movement, had to be able to sense up to 1.5 meters. To prevent the door flap from swinging loosely, it needed to be locked no more than 4 inches from its default closed position. The buzzer also needed to be loud enough for both humans and animals to hear, but not loud enough to cause damage. For this reason, we chose the sound pressure level to be between 70 decibels to 90 decibels. Lastly, the external battery had to be able to power the system for an additional hour if the power goes out.
For our project, our group strived for our IoT smart doggy door to be easy to use and to be reliable while also making the door as secure as possible. To achieve this, our group had to make some compromises which consist of the cost to create the product as well as the aesthetics of the doggy door. While the cost of production being high is a concern, this can cause the overall product to be higher in quality and accuracy.
Our plan of approach for this project was to break up all the required components to help compartmentalize our goals and objectives. Breaking up the project allowed us to easily direct our attention to individual tasks rather than tackling the project as a whole. This allowed for clear and defined tasks to be created as well as having the work distributed evenly. Because we knew that both the mechanical and electrical aspects would take a lot of time, both in precise measurements and acquiring components, we wanted to focus on those two parts first. For the mechanical aspect, the door had to be carefully constructed so that it could be easily installed and operated smoothly. For the electrical aspect of the project, due to the extended lead times when ordering components, we made sure to focus on our PCB right away so orders for parts could be placed as soon as possible. Providing ourselves with this cushion allowed us to test our electrical components and place any additional orders. For the software, we had to focus on setting up the back end first, which is like the glue to the system that holds the other parts together. This allowed us to test our embedded software on the system controllers and our software on the mobile application through its development lifecycle.
This is our hardware block diagram. For our project, we have a transmitter and receiver that will be communicating to a system controller that contains a camera, Wi-Fi, and a means of storage. From there, appropriate communication will be made to a buzzer to indicate status, some type of actuation to facilitate the locking and unlocking of the door, as well as a motion sensor that will be included for detecting the presence of a dog. A second system controller was needed in order to initiate the actuation as well as activate the sensors. All of this will be powered by an AC wall adapter, as well as an external battery backup in the event of a power outage. There is also a switching module that will initiate the change of power. Each member was assigned primaries along with secondaries.
Here we have the software diagram for our project. Our software setup begins with a user creating an account on the mobile app. Once they've done this, they can register their door using the serial number found on it and add animals that will interact with the door, along with sets of permissions for each individual animal. As can be seen in our diagram, these things all happen in an order on the app, but every step of the way is being recorded by the database. The workload split was decided in a way that both the front end and the back end were worked on individually with just enough crossover to ensure both ends are communicating without issues. To communicate with our solenoid driver circuit, we constructed a PCB that used a microcontroller to bridge the gap between our solenoids and the main system controller. The Arduino ATmega looked to be the perfect option for our project in every regard. The advanced architecture, combined with ease of use, along with the efficient power consumption and decent performance for its size, made it the clear winner for our team. However, for our main system controller, we went with a microprocessor as we knew our project had a lot of concurrent tasks to be handling at once. When deciding on just which one to use, the Pico was very quickly ruled out for its underwhelming power, and the Pi 4, while appealing, was more expensive and might have been beginning to reach unnecessary levels of power. When settling for the Pi 0, we knew that it was the right choice as it had just the right amount of GPIO pins, had onboard storage, camera support, UART communication, Wi-Fi capability, and just the right amount of processing power that we needed.
This is the pinout configuration for both the Raspberry Pi and ATmega 328P. Most peripherals were controlled by the GPIO pins located on the Raspberry Pi. However, the Pi had to communicate with the ATmega to control our solenoid driver circuit. The ATmega would actively listen to two GPIO pins on the Pi. Both devices were powered by 5 volts. The 3.3 volts on the Pi was used in conjunction with the GPIO pin to detect a button press. The Pi used UART communication to communicate with the reader. Motion sensor pins were actively listened to on the Pi to advance the running script. Lastly, the camera was attached to the Pi via a ribbon cable.
In order to create a design to power our project, we needed to consider the power requirements from each device. Our system has two voltage rails, 12 volts and 5 volts. The 12-volt rail will be powering the solenoids facilitating the locking mechanism. The 5-volt rail will be powering the rest of the project hardware. Regarding the PCB design, there was the choice between the AC to DC converter and the DC to DC converter. Ultimately, the AC to DC posed an interesting and involved design, allowing us to demonstrate a more impressive PCB than the DC to DC. Therefore, a 12-volt to 5-volt module was purchased for our DC to DC converter. All currents on this diagram are at the maximum ratings, ensuring that our design would be able to supply the power required. For our design, we chose the power supply unit to be our PCB. In order to design a PSU, we first needed to establish what topology we wanted to use. We looked at 3 different controller topologies: flyback, LLC, and PFC. There were certain trade-offs that needed to be made in order to find the best fitting design, making the balance between simplicity and efficiency difficult to find. LLC controllers had many advantages. Reduced electromagnetic interference, zero voltage switching, and zero current switching allowed for this topology to have high efficiency. However, the complexity mixed with the extremely high efficiency deemed this controller to be ultimately excessive for our design. Power factor correction controllers had a simplistic design, which offered an affordable PCB, but its small range of input voltages as well as its large and bulky design outweighed its simplicity. Flyback controllers therefore pose the best compromise between its advantages and disadvantages, with its simplistic design achieving acceptable efficiency from mutually coupled inductors. Here's the PCB design for the AC to 12-volt DC converter. The converter, inspired by Texas Instruments reference designs, is a flyback controller with quasi-resonance to increase the efficiency. The AC input is introduced on the left-hand side, followed by a mutually coupled inductor. A full-wave diode rectifier allows for positive cycles of the AC input to be passed through. Once the rectified voltage is smoothed out through an inductor and capacitors, a thermistor monitors the thermal properties at the rectifier's output. On the bottom is the high-power MOSFET controlled by the PWM driver chip, responsible for delivering current to the transformer, whose auxiliary windings power the IC through the VDD pin. This microcontroller will be discussed in more detail on the next slide. At the output of the transformer, the signal is smoothed out, leading to the 12-volt jumper that delivers a maximum current rating of 6.5 amps. As mentioned, the auxiliary winding of the transformer powers the IC chip through the VDD pin. Included externally at this pin is a holdup capacitor that ensures proper operation of the chip in the event of a loss of power from the auxiliary winding. The HV pin stands for high voltage. It is an input pin that takes the high voltages from the AC input in order to initiate an efficient startup current. The output of the driver, the DRV pin, controls the gate of the high power MOSFET. The VSense pin is able to monitor the input voltage from the transformer to the VDD pin, as well as the output voltage from the drive pin. The CS pin senses the current delivered through the MOSFET, while the SD pin is connected externally to a thermistor. The SD pin is pulled high by default. When the temperatures of the thermistors increases, the resistance decreases. So, once the SD pin is pulled low, a safety fault mode is activated as a result. The ground pin is for connecting the ground of the circuit to the IC's ground. This circuit is a solenoid driver, a second PCB we created that is responsible for the actuation of the locking mechanism. The circuit consists of 4 MOSFETs whose gates are connected to the Atmega 328P. In order to unlock the door, 2 solenoids lift up on either side, allowing for entry inside or outside. One pin of the Atmega connects to the gate of 2 MOSFETs that provide power to the solenoids. A diode is inserted in parallel with the solenoids to allow them to discharge. We need to include the crystal oscillator clock in order for the microcontroller to operate properly. This circuit also acts as our wire management center. It has 6 I/O pins for the 5-volt rail. The I/O pins located on the top left are for the 12-volt power, as well as the solenoid connections and Raspberry Pi GPIO pins. One of the Pi pins will activate the buzzer when necessary, and the other 2 Pi pins will be for communication to the Atmega with respect to the activation of the inside and outside solenoid MOSFETs. The power supply for the project is meant to switch between a wall adapter and a battery bank in the case of a power outage. The power bank that we chose as our backup was a rechargeable 12-volt lithium-ion battery with 8300 mAh. The battery has a 12-volt 6-amp barrel jack I/O port that will be used to power the project. In order to switch the source of power between the battery bank and the wall adapter, the switching module will output the voltage of input 1 by default. Once the voltage drops below a certain level, input 2 will be switched on.
The majority of the Doggy door is constructed using 8-inch by 3/4-inch wood planks. This consists of the outer walls, the floor, the ceiling, as well as the box on top that will house the hardware components. The inner walls of the Doggy door is made up of 1/4-inch wooden sheets and has a gap in between the larger wood planks to house the locking mechanism. Additional wood is placed in between the 2 types of wood to close off the gap between them to protect the locking mechanism from weathering and being tampered with. The door flap is made of polycarbonate sheet and was chosen because it's lightweight, has an impact-resistant surface, is shatter-resistant, and has UV protection for long-term weathering. On top of the door contains a compartment that is used to house the remaining hardware components that consist of both the PCB, antenna, RFID reader, external battery, and etc. The front door has a port that is located on the top left part of the door that can be used to charge the external battery that is housed in the top compartment. Each side of the door has a motion sensor, and when motion is detected and the tag is within range, it will query the database and retrieve the corresponding information and unlock the door accordingly. The front side of the Doggy door also contains a button in the top right corner and is used to register new tags. This is done by holding the tag within range of the reader and holding down the button for 3 seconds. A camera is also on the back side of the Doggy door above the motion sensor and is not shown in this picture. When motion is detected outside, regardless of whether or not the tag was within range, the camera will take pictures and send them to the Doggy door application. This is done to provide a picture of the owner's dogs as they exit through the door, as well as a security precaution in case there are wild animals and intruders outside. The locking mechanism consists of 3 pieces that were designed using AutoCAD and then 3D printed. It also contains 4 solenoids that will be used to unlock the door. These 3 pieces consist of 4 locking pins, 2 knobs that are attached to the end of the door flap, and 2 shafts that house the pins. Each pin has a slant on it that faces outward on each side. This allows the knob to push up the pin and once this happens, it will be stopped by the next pin and be locked in between the two pins. A solenoid will be attached to each pin, which will allow the pin to be pushed up to allow the dog to exit through the door. This process is triggered by the dog's tag being read by the RFID reader. The locking pins are also set up to only allow the door to work in one direction at any given time. This prevents the dog from exiting through the door and other animals coming in right after. While researching different methods to lock and unlock the doggy door, a few different things were considered. One of them was the 3D printed locking mechanism, as well as the solenoids that our group decided to use for the final prototype. The other considered was a linear actuator, which would be placed above the door and would be used to open the door vertically. We decided not to use this approach because it was costly and the movement speed was only 4.5 millimeters per second. The other device considered was an electromagnet, but this was not chosen since it could interfere with the RFID reader and antenna.
IoT projects utilize a database to store all information that will be accessed by users. With a good database setup, we'd be able to easily offer customer support and be able to send out over-the-air software updates to have the project evolve over time. In contrast to storing everything locally only, users can access their system through the mobile app from wherever they are and make whatever changes they like as long as they have an internet connection on their phone. With Firebase, the decision we went with, we can give our users real-time updates to whatever changes they are making, while also having everything being watched and noted if the systems go offline. In the early brainstorming stages of our project, we realized that sometimes on the outside section of the door, you may have unwanted guests. Putting the peace of mind of our consumers first, we decided to add a camera that could capture any critter that might pay your door a visit. Our camera works in conjunction with a motion sensor. Images are taken when any motion is detected, and then they are sent to the database storage, which allows them to be displayed on the user's mobile app. When deciding on which camera to go with, the options we were looking at weren't too different from one another. The one we ended up with was cheaper while also having a good angle of view. The low image quality was not of our concern, as we aren't using the camera for our user to have new pictures to post on their Instagram. Passive infrared sensors were selected for our project because sometimes inanimate objects might be placed by the door and we do not want to send out a signal when such is the case. The outside sensor picks up motion and alerts the camera when it knows that it is a moving, living thing. It then alerts the reader to begin to scan for any tags in the area so that the system checks the permissions of any nearby registered pet. We use a combination of two motion sensors along with local data to keep track of whether each animal is inside or outside. With the range, good field of view, small form factor, and low price, the decision we went with was a no-brainer.
For the mobile application, we decided to use the React Native command line interface, which allowed for cross-platform development. Due to our previous experience with React Native, this allowed for faster development and allowed us to focus more on the features of the application. The purpose of this application is to allow the user to interface with the door and to control it remotely. When the user first opens the app, they are prompted to either log in or register an account. When you register an account, you need to provide a valid email, password, and the serial number of the door. The serial number is given to the user and is required because this will allow the door and the mobile application to be linked together through the database. Initially, the home screen of the app is empty until you register an animal by scanning a tag via a physical button on the door. Animals registered can have the following changes made to its profile: name, breed, profile image, state, passage permissions, allowed during rain, as well as curfew. Finally, an animal's profile can be also deleted. Also, from the home page, images can be viewed that were taken by the system within the last 24 hours. Anything over that time frame is automatically deleted.
We decided to choose RFID as our wireless technology as opposed to Bluetooth, GPS, and ultrasonic sensing. This is because RFID has fast read rates, consistent communication, and can allow for callers without batteries. RFID offers 3 different operating frequency bands: low, high, and ultra-high. Ultra-high frequencies can read up to 30 meters or more, giving sufficient read ranges that low and high frequencies cannot. Low frequency has the advantage of its low susceptibility to electromagnetic disturbance, but unfortunately it has slow data processing, as well as too short of a read range for our application. High frequency transmits information faster, with low EM interference as well, but still, its read range is too short. Therefore, UHF was the frequency range we settled on. However, we needed to be careful with its interference susceptibility. Luckily, we are enclosing our reader in a wooden design, which does not pose any issues. Next, the type of tag needed to be discussed. Active and passive are the two main types of tags, where active tags initiate communication between itself and other devices, requiring a battery to be powered. Because of this, these tags tend to be more expensive, but they do have longer read distances for the same reason. Passive tags, on the other hand, do not initiate communication, but rather wait for incoming signals, requiring no internal source of power. Due to the cheaper price, no battery, and sufficient read range for our application, we decided to utilize passive tags. The tags must adhere to the ISO 18006C protocol standard. Within this standard, there are 6 classes. Class 0 is a read-only passive UHF protocol. Having the tag as read-only prevents the ability to add additional information that can assist with animal-to-owner identification. Class 1 is a write-once, read-many UHF or HF protocol, which is perfect for our design, considering we only need to write once and it falls within our frequency range. Class 2 has an indefinite read-write operation with passive tags, but we only needed to write once, making this class unnecessary. Ultimately, Class 1 was the category that our project fell under. For our reader and antenna, there were some important parameters we needed to consider. For the reader, it needed to support an external antenna, UHF, and be budget friendly. The only reader we found that fit this description was the M60 Nano. For the antenna, we know that we needed circular polarization, which allows for the antenna to read tags at any orientation. We needed a beam width of around 120 degrees in order to have an appropriate reading area. The read distance we wanted was over 1 meter, but this variable was flexible, where the power delivered to the antenna could be lessened in order to achieve a lower read distance. As far as the cost goes, of course as low as possible. The frequency range was established earlier as UHF. The chart shows a few antennas that we considered. The Time7 slimline antenna seemed to be the best fit, seeing as its beam width was the closest to what we were aiming for.
This is our proposed budget for the project. We knew the RFID was going to be the most expensive component, making up the majority of our expenses. The other components like the sensors, camera, and battery added up over time. Around $600 was estimated for our project.
Here we have our team's division of work. Logan and I were in charge of a lot of the software side of things, with storage, Wi-Fi, database, and so on. Jordan was mainly responsible for the construction of the door and designing and building the locking mechanism. Hunter was responsible for the RFID research as well as designing and constructing the PCB and PSU.